Okay, so we're going to continue with chapter 6 tonight. But I want to make sure that everyone is comfortable with this idea of a probability distribution and then the special ones that I'll be covering. Right, so I'm going to do a little bit of a review. See, actually, we'll go back to 6.1. Maybe you should do that first and make sure that you're all good with probability. Now, random variable, everybody good with that? What a random variable is? It is a variable, just like you saw in algebra. And it can take on, if it's a discrete random variable, it can take on a limited number of individual values. So picture a number line, we'll call it the X number line, and it only can take on a certain number of points on that number line. Not an unlimited number, just a certain limited number. And that is, and a random variable means we're not sure ahead of time which of these individual values will show up when we run a probability experiment, all right? It's random. Each of those individual probability, each of those individual values of a random variable has an associated probability. Now, there are some probability experiments where the probabilities are all equal to each other, such as flipping a coin or rolling a die. Okay, all the individual outcomes are equally possible. And then there are other random variables where the probabilities are unequal. Okay, there's no need for them to be equal. All right. A continuous random variable is something we'll deal with next week. And that is a random variable that can take on any value in between two endpoints. In other words, in an interval or range, any value, all right? An infinite number of values it can take on. And these types of random variables are usually the ones that are measurement variables, the ones that we're measuring things with, like temperature and height and weight, things like that, all right? So those are continuous random variables. We're dealing strictly with the discrete ones first, because they're easier to understand. All right, and then, you know, they gave a simple example of a discrete random variable, flipping a coin, maybe flipping a coin twice, okay? Now, when you flip a coin twice, you end up with 4 possible outcomes. That is, both are heads, both are tails, or the other 2 possibilities are heads first, tails second, tails first, heads second. All right, there's 4 individual possibilities. The probabilities associated with this particular random variable of flipping a coin twice has, for the 2 heads and 2 tails, 1/4 probability of each one of those, right? Only one possible outcome. And then having 1 head out of 2, there are 2 possible outcomes for that of 1/4 each, which means 1/2 is the probability of that event. Okay? So that's the probability distribution. We call it a probability distribution. It's a list. When we say distribution, it's a list of individual values for the random variable plus their individual probabilities. That's what we mean by a probability distribution. Okay? All right. This is a probability distribution here. All right. We could, of course, say that the random variable is the number of heads in the flipping of 2 coins. So you have up to 2 heads, right? You can have 0 heads, 1 head, 2 heads, and that's it. So there's 3 possible values for the random variable, x, which represents the number of heads in 2 flips of a coin, are 0, 1, and 2. When we have no heads, which means we have 2 tails, the probability is 1/4. When we have 2 heads, the probability is also 1/4. But for 1 head, There's two possibilities. The first flip of the coin is head, or the second is the head. And that's why the probability is 1/2. Okay? So we can explain many times why the probabilities are what they are. Okay? This is a probability distribution, a list of the values of the random variable x plus the corresponding probabilities. Okay? All right, Mo, are you good with that so far?
Yeah.
Okay. Now, we can come up with all sorts of examples of this, right? Give examples of random variables. We define what they are, and then we determine, maybe we don't figure out the probabilities, maybe they're given to us. The important thing is, number one, that each individual probability is between 0 and 1, which by definition it is, right? And that the sum of the probabilities are equal to 1. Okay? So all probability distributions have that those two criteria, that the probabilities are between 0 and 1, and that they add up to 1. Okay? Is that clear also? We can also represent probability distribution through something that looks like a histogram, where each bar is centered around the individual values of the random variable. In this case, the number of heads in 2 flips of a coin. And the height of the bars are the, we can call them relative frequencies, but they're basically probabilities. They mean the same thing. 0.25 for when x is 0, 0.5 when x is 1, and 0.25 when x is 2. So we can represent it like this also. Book goes into 4 criteria. I mean, I mentioned 2, right? I mentioned criteria 1 and criteria 4 for a discrete probability distribution. 2 and 3 here are just technical details. That is, we're considered, when we say x, values of x are exhaustive, that means we have listed all possible values of x. We have not excluded any at all. And they're mutually exclusive from one another. It's not, in other words, one of the values, it's impossible to have one of the values and at the same time have another value. All right, they're mutually exclusive. So they're mutually exclusive and they're exhaustive, meaning that we've considered all possible values. All right. So you can consider these for a discrete probability distribution be the 4 criteria. When we get to continuous random variables, these 2 in the middle here are slightly modified because of the fact that we're dealing with unlimited number of values. So we'll get to that, next week. All right. Sometimes a word problem is given where we can determine the individual values of the probability distribution. For example, here, I don't know if you can or not. Let's see if we can. It says a financial counselor conducts, I think we went over this last time, conducts investment seminars with each seminar limited to 6 attendees. Because of the small size of the seminar group and the personal attention each person receives, some of the attendees become clients following the seminar. For the past 20 seminars she has conducted, X, which is the number of attendees who become clients, has had the relative frequency distribution below. Now, because there are 6 people in the seminar, the number of people who become clients can easily be listed because either no one becomes a client, right? We list all possibilities, right? If X is the number of clients, 0 has to be one of the possibilities. Nobody becomes a client out of the 6. 1 person becomes a client. 2 people become clients. 3 people can become clients. 4 people can become clients. 5 or 6. Now, in this case, the probabilities, however, are not predetermined. Okay, they're not predetermined. The reason why they came up with these probabilities is because of their experience, long-term experience giving these seminars, all right? And they did a relative frequency calculation or estimate of these probabilities. All right. Basically, they determine how many seminars that they have, and how many of them had had 0 people starting, and how many did they have 1 people starting, like that, right? And then whatever frequencies they come up with, they divide by the number of seminars they've given over time, and that gives the relative frequencies, and they are estimating these probabilities. So this is the relative frequency approach. This is not the classical approach for probability. All right, is that clear what's happening here? And so these probabilities have to be given to you. All right, they're given to you. All right. Okay. So that's a probability distribution there. So if we wanted to ask a question such as, if a seminar is selected at random, what's the probability that there are at least 3 of the attendees who become clients? And what would be your answer? So if you have a seminar, you pick a seminar at random. I think that's what I said. Let's say it again. I pick a seminar at random. What's the probability that the seminar had at least 3 of the participants becoming clients?
65%.
That's correct. Right. You add up P3, P4, P5, and P6. So you see how it works? It's pretty easy, right? There's nothing unusual about this, all right? But remember, these are relative frequencies here. These aren't classically determined. I mean, we could have classically determined it, right? We could have done that if we wanted to, but this was based on experience giving these seminars. The mean and variance, we went over that last time also. The mean is simply the sum of the products of the individual values and their corresponding probabilities. Right? We simply multiply each value by its own probability and then add up those products, and we get the mean. The variance is the sum of the square of the difference between the individual random variable values and the mean. So you have to calculate the mean first, determine what that is, and then for each individual value of your data set, you subtract the mean from that value, and then square that deviation, and then you multiply it by what? The individual probability for that value. And when you do and add up all those products, you end up getting the variance. And just like any other definition of standard deviation, you just take the square root of the variance and you get your standard deviation of the probability distribution. All right. Any questions about that? We used a Excel spreadsheet that last time, right? Okay. And it shows an example here from the one that the one with the seminar problem. So 3.2 attendees is the mean. The variance is 2.66. We took the square root of that. We get 1.63 attendees who become clients. So what they're saying is that the average number of clients is 3.2 over the long term, the average number of clients per seminar, and the spread of these individual values, it's approximately 1.63 between the individual values. Okay, that's the average spread between those values, 1.63. All right, now we'll skip this uniform thing here, because what the uniform thing distribution was talking about was that many times the probabilities are equal to each other, right? You know, an example of that obviously would be a lottery, where each of the balls that are selected have the same probability of being pulled from the bin. Okay. Now, so we can create these probability distributions. You can even make them up if you want. right? You can make them up as long as each individual value is between 0 and 1 for the probabilities, and they all add up to 1. You can have any x's here that you want, right? It doesn't have to be from 0 to 4. It could be any numbers. It could be, you could be, for example, if you were an economist, right? Let's say you were trying to predict GDP for the next year, right? GDP, some number, all right? And you have 3 different economic scenarios. You have slow growth, you have moderate growth, and you have high growth, okay? So you'll end up with 3 different, what? 3 different GDP values, depending on which of those things materialize. All right, that's your prediction of what GDP will look like in the next year. Then you assign probabilities to each of those economic scenarios. You come up with some method for doing that. As long as the probabilities add up to 1, you have a probability distribution. The GDP numbers are the x's. So you could see, you know, could have a 20 here, you know, which may represent 20 billion or whatever the number is, 20 trillion. For 1, so for 0, the first one could be a slow growth. Then you could have 50 next to it for moderate growth. And then you could have, for high growth, you could have 100, whatever the numbers are. And then you have your probabilities, right? And maybe the slow growth has 60% chance of that based on your modeling, 30% chance of moderate growth, and 10% chance of fast growth, all right? Then you can simply figure out the mean and standard deviation, right? And you can report that to the media. You know, my overall average forecast is, and there you give it, right? That's maybe how they do it. They might be doing it by looking at scenarios and then taking probability weighted scenarios. You know, they're weighting each of those scenarios by their probabilities, and they come up with an overall average forecast. And that's how they report it. Okay, so the x's don't have to be these numbers here. It could be any numbers, anything, as long as they're numbers, right? So the x's could be any numbers. Now, let's, and I mean, here's an example right here, right? I mean, this with the flood, remember we talked about that, you know. There's other examples here that you can certainly look at. Now, and there are examples in the handout that I'll be giving. Now, there are special discrete probability distributions. They are special because they meet certain criteria. In other words, when you see this type of scenario, they have special formulas for determining the probabilities. All right, there's a formula for it. In the discrete world, and they're called probability density functions. That's the overall name for them, probability density functions. And they calculate the probability of one of these values occurring. So instead of using relative frequencies, instead of using a classical approach, you have a formula for the probabilities. And the formula is dependent upon some function of x. Some function of x, typically, okay? So let's take a look at the binomial. Now, the binomial deals with what's called the Bernoulli process. Bernoulli was a famous scientist, right? He was not just a mathematician, he was a chemist, right? I believe there's different things in chemistry named after him. Long time ago, he was alive. What's a Bernoulli process? It means it's like flipping a coin. Bernoulli process basically says there's 2 possible results, okay, when you flip a coin. When you roll a die, a Bernoulli process says one could be a 2 and the other's not a 2. In other words, there's 2 possibilities. That's Bernoulli. Very simple. Binomial is a repetition of the Bernoulli process over time. Okay, so obviously one of the requirements is that you only have two outcomes, possible outcomes in a binomial. All right, two possible outcomes. That's the number 2 here. There are actually how many? There's 4 criteria. So these are special criteria for the binomial. There are only 2 possible outcomes. So all these other ones that we've been looking at have had multiple outcomes, right? Not just 2. There's 4, 6, whatever, right? They all have multiple outcomes. But in this case here, each trial or repetition of experiment has 2 outcomes. But you can have multiple outcomes. You know, I mean, if you were taking a survey and there was 5 possible answers for a question on the survey, that's not a Bernoulli process, right? That's not Bernoulli because there's 5 possible answers that you can get. You had 2 possible answers, that's Bernoulli. Okay, does that make sense? So each trial has 2 possible outcomes. We usually call one of them a success, the other a failure. And the only reason we say that is because the one that we're usually only interested in one of the 2 outcomes. So we call that the success, and we call the one that we're not interested in the failure. All right. Now, this binomial has at least 2 consecutive trials, at least 2, usually many more than that. So each trial, 2 possible outcomes, and the binomial has many outcomes, many trials. The trials are considered statistically independent. Okay, that is, the outcome of one trial is not affected by the outcomes of the others, such as flipping a coin. If you flip the coin once, you flip the coin again, the second flip of the coin has completely independent of the first flip of the coin, right? There should be no knowledge or information that's carried over from the first flip to the second flip of the coin. You agree with that? The only reason that one flip could be dependent on the other is maybe you would flip the coin 1,000 times, your arm is getting tired. Okay, so maybe there is something that's affecting your current flip of the coin. But assuming your arm is in perfectly good shape and you keep flipping the coin, then each flip of the coin is independent. All right, and the fourth thing, and this is very important part of it, is that the probabilities of success and consequently the probability of failure are the same for each trial. Okay. Now, when you flip a coin or roll a die, it's true, isn't it? Every time you flip a coin, you're going to have 2 outcomes, right? 50-50. Same thing with rolling a die. 1/6 outcome for any one of those dots, any of those faces. 1/6 outcome. Does this have to be true all the time? We're going to get into something, a subtle little thing, because the binomial is used in statistics. However, and one of the requirements, what you'll see a little bit later on, is that each time let's say we run a survey, each time we ask the same question, we're going to make the assumption of independence between observations. We're also going to be assuming the same probability for each of those observations. Is that really true in reality? And I'm going to be bringing up to you this idea, and I guess I could bring it up to you now, is that there's 2 types of sampling. It's in the book, but it's an important concept in statistics. One type of sampling is called sampling with replacement, and another type is called sampling without replacement. Sampling with replacement, let me give you an example of what that is. Suppose you have an urn with 3 types of colored tennis balls. All right, maybe there's a green ones, and then there's orange ones, right? Green and orange, and maybe there's the traditional white ones, all right? So suppose there are, let's say 6 green and 4 white balls and 10, what's the other color I said? Orange? Let's say orange, all right? So let's remember that. 6 green, 4 white, and 10 orange. There's 20 balls in there. Suppose we pick a ball at random. What's the probability that it's a green ball? Now, how many green balls are there in the urn?
6.
How many balls are in the urn?
20.
What's the probability?
6 out of 20.
Yeah. All right, 30%, right? Is that right? 30%. What if I put the ball back and I ask, what's the probability that I pick a second ball and it's a white ball? What's the probability? Remember, there's 10 of them, right?
Okay.
Did I say 10? No, there's 4 of them. So what's its probability?
1 in 5.
All right, 4 out of 20, 1 in 5. Now, let's rerun that experiment. We take one ball out. It's green, right? And now we keep it out. What's the probability now of getting a green ball on the second try?
5 out of 19.
5 out of 19. Now let me ask you a question. Is that second time, that second ball we take out, is that the result dependent upon what happened with the first ball?
Yes.
Yes. The probability has changed because we have taken out a green ball, leaving only 5, and we've let the ball out, so there's only 19 total balls in the urn. That is those two events are dependent on one another. They're not independent. Probability has changed now of the green ball, hasn't it? And actually, whatever the probability of the other balls were, they all change also, right? Because now there's 19 of them left when you keep the ball out. So this last thing we did is called sampling without replacement. Sampling without replacement leads to dependent events, consecutive events, with probabilities changing over, right? From one trial to the next. The one that we did earlier, where we put the ball back, is called sampling with replacement. So let's think about a survey with 1,000 people in the survey. When we sample people that way, is that sampling with replacement or sampling without replacement? When we go from one person, one participant to the next participant, asking the same question, are we sampling with replacement or sampling without replacement?
My guess would be with replacement, because one person's answer, probably, like if it's an ordinary survey, wouldn't affect anybody else, the next person's answer.
Okay. Well, you're saying there's some independence there, but is it sampling with replacement, sampling without replacement? Han, what do you think? Or Mo? You can answer also if you'd like.
I agree with Steve.
Okay. Mo, what do you think? Don't tell me this is a herd mentality that's going on here.
Yeah. I guess I'm just kind of confused on what replacement means, because I think that Steve is right, but then you keep on talking in a tone that makes me think that it's not. So I'm gonna go without replacement.
Well, wait.
The tone of voice, right?
Yeah, I agree with Mo on that assessment. But I guess, I mean, if you're using,
I should have been like a
possible
machine or something, you know. I have to have the computer ask the question.
I guess I would change my answer to say if you're using up your survey answers with each question that you ask, then you're not replacing them. So there's not replacement.
Well, think about what the balls, okay? Sampling with replacement, and it's simpler than what you think. And the urn, sampling with replacement, you pull the ball out and you put it back in. Think of the urn as a population of balls, tennis balls, all right? So once you use one of them, you put it back. Sampling without replacement says you pull it out and you don't put it back. Think of a survey. When you sample from a survey, you're pulling people out of the population. Once you're done surveying somebody, do you say, all right, we're going to put you back into the population and there's a chance we're going to survey you again? No, that's not going to happen. It's sampling without replacement. That's what survey naturally is. Any type of sampling is survey without replacement, all right? Because you're not going to reuse.
I think we should.
Go ahead.
I mean, I think the balls are more like the questions instead
That's
of
interesting.
the
I agree there.
No, we're talking about sampling. We're not talking about asking a question. All right, we're talking about selecting. For example, what if we're selecting the balls and then our experiment has to do with how spherical the ball is? Okay, we're measuring. Let's say we're measuring the diameter of the ball, and we have this really precise measuring instrument that sees that there's a slight variation between the diameters of each of the balls. Okay, so that's what we're interested in. We're not interested in anything else than that. However, in our selection process of which balls get to be measured, we're doing a sampling process. We're choosing those balls to be measured, their diameters measured, whatever we're doing with those things. The same thing with the survey. We're selecting people, and I don't care what we're doing with them. We could be doing questions. We could be asking them to pull hairs out of their eye. It doesn't matter what we're asking them to do. The selection process happens before the experiment. Okay, you see what I'm saying? When they're talking about in the book sampling with replacement and sampling without replacement, they're saying the selection from the population of a sample of things. And that's it. Measurement has not happened yet. Questions have not been answered yet or even given yet. It doesn't even matter. At that point, it doesn't matter what you're going to be doing with those individual things that were sampled. We're simply looking at the sampling process. And therefore, and I'm trying to get you to think, real clearly about this. There's two types of sampling. You're either going to reuse, if you're going to be measuring something or whatever you're going to be doing, right? You determine this ahead of time. You're going to say, all right, once I ask somebody a question, once I measure their height or whatever it might be, they're done. We're not putting them back in the pool into the population saying, all right, there's a chance that you could be selected again. Just be aware of it. And I know it's annoying, but we may have to ask you the same question again. And they're going to look at you like, what's wrong with you, right? Why would you want to do such a stupid thing, right? And you say, well, that's because I have to make sure it's sampling with replacement because then my individual probability, and they're going to look at you like, I don't really care what your reason is. I'm not doing that, all right? So in real life, when you select people, or even fish, right? I mean, I guess you could throw the fish back into the pond, but you're usually going to be doing sampling without replacement. Now, here's the problem. When we get to part 3 of the course, when we talk about inference, all the inferences, everything that we do assumes that the probabilities do not change from trial to trial. And yet, the process that we're using does change the probabilities from trial to trial, just like with the balls. So the question is, why can we use these procedures that we're going to be using if they don't meet the criteria that not only of independence between observations, but the probabilities have to be the same. Can you think of an answer for that? How
Could
can
you
we,
repeat that question? The connection was spotty.
all
so
right,
you-
let me say it again. Since we're dealing with, in most cases, I'd say 99% of the cases when we sample, we're dealing with sampling without replacement. And yet the statistical procedures that we're going to learn how to do require sampling with replacement. How can we possibly do these procedures? Can you think of a reason for this? And there is a good reason. Think of numbers, the nature of numbers and how they change.
Right.
That's your hint. We'll see if you, because I'm trying to get, I'm not, if I just said this out loud and you were writing it down, I'll assure you won't remember it. And it's a critical issue in statistics. Statistics, if it wasn't for this issue that I'm talking about here, statistics is a waste. You just throw it all out, right? We'd just be collecting a bunch of numbers and that's it.
Well, to answer the question, I don't know if this is right. It's sort of a guess, but we rectify doing no replacement because you need to do these without replacement to establish a probability, because that's, you're sampling the population with the intent of establishing a probability based on experience. And if you're naive about a population, you can't assign a probability to any particular person or, survey subject. But
Sure you
after you do that, you can.
Sure you can. Sure you can. You can assign, if you have a list of people, let's say you have well, what did we call it before? A sampling frame, right? Suppose we had a list of people, an actual list of people in the population. And we want to make sure that each person is equally weighted in being selected for the sample. Okay, let's assume that. So let's say there's a million people in the sampling frame, right? There's a 1 out of a million chance that you're selecting one of those people out of the population, right? It would be true if we had a real random process, it'd be true for any of those million people. What I'm saying is once you choose someone out of there and we do something with them, right? Whatever we're doing, measuring this or doing whatever, it doesn't matter. I want you to think about the process itself. We're not going to reuse them again, most likely.
Mhm.
So if there's a million people there, what's left? 999,999 people. Has the probability changed for selecting the second person? You bet.
Yeah, but not by
How
enough.
come,
To
and then
affect
what my question is, how come we can assume sampling with replacement when we're actually doing sampling without replacement? How can we do that?
because the number is so large that if you don't do the replacement, it doesn't matter because the probability changes by such a little amount.
That's it. That's it. That's why I wanted you to answer this question and not me just to tell you. All right, because in a typical statistics course, you're going to read it. So your professor will just say it to you and it'll go into one ear and out the other because it doesn't sound that important and you won't remember it. But that's the reason. You want to make sure that the sample size is large enough so that when you do select somebody, the probability of selection of the second person has not changed, hardly has ever changed at all.
Does that change if you're taking a census? That like attitude?
Yes, well, it's, it's not as important with a census because if you do have a census, you really contact everyone and then there's no inference that's going to go on. You have the population.
Right. Okay.
Yeah, it's not as important, right? But it is important for drawing a subset of the population because we're not sure if whatever we are coming up with really is precisely representing the population, right? It could be off. So, and it probably is off. It's probably not the same as the population value. We're taking the mean of heights or something. Or, if we out of those million people, if we just have a sample of 100, the mean height, and we're measuring the height of the 100 people, the mean height is probably not going to be the mean height of those 1,000,000 people. See what I'm saying? So we need to know when we're sampling, because one of the things you'll learn is that this inference that we're going to be doing, inference means taking the sample results and applying them to the population. We have to make sure that we meet the criteria for inference. And one of the criteria for inference is that the probability of selection is equal. And what you just said a minute ago is the reason why we can assume it, even though it's not true. We can assume that the probabilities don't change because they change by such a little amount that in essence, we can assume sampling without replacement. See what I'm saying?
Yep.
So if your sample size is too small and the probabilities change dramatically, that's a problem. It's not considered very often, actually. You know, you'll see problems where, you know, you have a sample of 30 people, right? And then you know, one person selected, you know, each one of them has a probability of 1 out of 30 being selected. Well, once one person's used, then there's only 29 left, and you have to use your calculator and say what's the decimal of 1 divided by 30. Well, that's 0.033. If there's 29 people left, what's 1 divided by 29? Well, that's 0.034. You may think, all right, that's close enough. That's close enough to assume those two probabilities are equal to each other. See what I'm saying? You have to really think about that, because all the procedures are assuming that you're selecting people at random. Because if you're not selecting people at random, you cannot do inference. Because inference depends on that, selecting people at random. Every procedure we will learn in this course and any future courses that you take, I don't care what it is. I don't care how advanced it is. They all assume random sampling. And if you don't do random sampling, then you better have some other method that works, that allows you to take the results of your sample and apply it to the population. Otherwise, you have a nice information about a sample and that's it. It only applies to that sample and doesn't apply to anything else. Okay, so it was a drawn out explanation, but I wanted you guys to figure this out, because this is the critical aspect of what we're talking about. Okay, now the binomial requires the probability of each of those trials, which are independent of one another, to be the same. That's why we use this. You'll see in one of the models that we'll be using in the future. However, if the sample or the number of trials is small and the probability does change, in other words, we do use sampling without replacement, then the binomial is no longer valid. There's another distribution that we will be using, okay? And it's called, now, the hypergeometric. The hypergeometric is like the binomial. It's just as similar to it in all ways, except for the fact that the observations are not independent of one another because the probabilities change, or vice versa, whichever way you want to look at it. They are dependent. Each trial is dependent on previous trials because you're doing sampling without replacement. Okay? So let's go back to the binomial and just take a look at it once again. And remember, I showed you how to do this in Excel, right? How to calculate binomial probabilities in Excel. And the equation is this thing here. N represents the number of trials. X represents the number of successes that you're interested in, right? Out of those N trials.
I'm not seeing anything.
You don't see anything? You don't see anything, Steve?
I can see.
I can see as well.
Okay. Sorry, Han. Why can't you see it?
Why?
Well, if you put your hand in front of the screen, I don't think I can't see it either. I can do it.
No,
I'm
no,
always-
that's
I'm
my
always-
camera.
It's your camera. Okay. Okay. Sorry. But this is in your book anyway. Just open up your book if you have your book in front of you. N
Okay,
factorial.
okay. I have it.
Yeah, it's that formula. Now I'm using p instead of pi because small p, it's a probability of success, but in the book they use pi as the probability of success in any given trial. Notice also that for the binomial they have special formulas for the mean and variance. So you don't have to go through those multiplications that we were going through before. The mean is the number of trials times the probability of success. In that Excel spreadsheet that I've created, and I don't know if I posted, but I will post it. You will see, you could try it the long way and then just use the formula n times the probability of success, and you'll see that it will match the mean. The variance is simply n times the probability of success times the probability of failure. And therefore, the standard deviation is the square root of that. So if I was asking for the standard deviation for a binomial, it would be the square root of n, the number of trials times the probability of success times the probability of failure, all inside the square root. Okay. Here's this whole thing about sampling with replacement, sampling without replacement. Binomial obviously is sampling with replacement. All right, that's what it's assuming. All right. Notice what it says here. All right. It even says it here in this thing here. If the sample size is large enough, let's say we have a binomial situation, but it's in a survey question. There's two answers, right? There's two answers. Maybe Trump versus Biden. All right. Let's say there's a binary choice between Trump and Biden. Who are you going to support, right? Well, again, you have sampling without replacement, but if the survey is large enough, you're going to assume sampling with replacement, and therefore you can use the binomial to come up with your probabilities. So, if you ask 1,000 people, who do you prefer, right? And what do you need? You need the probability of success, right? Probability of failure. Maybe you want this probability of success to be 0.5, right? Because you're not sure. In trial, right? What if 550 out of the 1,000 choose Biden? Okay. If you're doing sampling without replacement, that's not binomial. But if the probabilities don't change that much from trial to trial, then you can assume sampling with replacement, and therefore you can use the binomial. Okay, get the idea? You see what I'm saying? I want you to realize this now before we actually do those procedures later. All right. Now, let's go to the hypergeometric. And I think what we're going to do, oops, it's like I lost it. So I have to, see if it opens up for me. I might have to log in again. No, here we go. Can you see this page, what I just did?
I can see it.
All right. Let's go to the hypergeometric. The hypergeometric, the only reason I want to show this to you is because it is like the binomial, and yet it assumes that probabilities, the consecutive trials are not independent, and the probabilities do change over time. And this is the formula that, this is what it looks like. It's a little more involved, but it's not that hard to understand. N is the size of the population that you're drawing the sample from. That's big N. Small n is the size of your sample. Okay, people you're drawing from. S is the number of successes in the population. You should know that ahead of time to do this. All right. Now, here's the issue. You can't use the hypergeometric in sampling. Why? Because you don't know the number of successes in the population. If you're doing a poll, or reason you're doing the poll is to find out, you're estimating the number of successes. Then you're determining how many people are going to vote for Biden. Well, you don't know, right? You're estimating it. So you don't know S. See what I'm saying? So this hypergeometric is only used for small populations that we can determine things ahead of time. We know the number of successes in the population. X is the number of successes in the sample. That's what we usually know. And this is the formula using combinations. In the numerator, we have the combination of choosing X out of S. That is X successes out of a total of S successes. The second combination, which is multiplied in the numerator, is we're taking the population size and subtracting the number of successes, and then the sample and subtracting the number of successes out of the sample. That becomes this one, and then the denominator is simply that out of a population of n, how many combinations do we have of samples of size n? That's what this is in the denominator. The mean is this formula. It's n times s divided by big N. And the variance is this really complicated looking thing here. All right, don't worry. What I want you to see when we do problems, and we'll do them next week. Next Tuesday, we're going to spend the whole session doing problems on all three of these probability distributions, so that when you see a word problem, you'll be able to recognize which one you're looking at. Now, the final one I want to show you is called the Poisson distribution, named after, why is it doing that? It's so annoying. I don't know why it's doing that. Cengage is acting up on me here. Let's look at the Poisson. Now, the Poisson is important in counting the number of times an event occurs if the event itself has a small probability. Okay? Poisson. It is discrete because you're counting the number of times the event occurs, but it doesn't occur very often. Now, number of trials. Theoretically, there's no limit to the number of trials here. So when you do Poisson probability questions, they have to limit the number of possible trials in the problem itself. It'll be limited, all right? It'll be limited. But here's examples of what Poisson is doing here, the probabilities. For example, customer arrivals at a service point during a given period of time, such as the number of motorists approaching a toll booth, the number of hungry persons entering McDonald's restaurant, number of calls received by this is old here. There's no, you don't have switchboards anymore. A call center, all right? You see what I'm saying? It's dealing, you're dealing with the number of things that are occurring over time, okay? This is used quite frequently, all right, in many different areas, Defects in manufactured materials. You may want to know the number of flaws, all right? So questions about the number of things is what Poisson deals with. A number of work-related deaths. I think insurance companies are interested in that, right? Estimating that. The number of births, deaths, marriages. They're estimating these things. That's what this what this distribution is, the X part of it. And then the probability is a formula. And it looks kind of fancy. This is the formula. Now, do all of you know what E is? You should have learned it in high school mathematics. E. Yes, you know. Yes. How about Mo? Mo, you know what E is? The
I'm sure
number
I did
E?
at one point, but I do not anymore.
2.718 continues forever. It's like pi, the universal irrational number that's used everywhere. All right. Statistics, engineering, I don't care what field, you're going to see E. All right. It's universal. It's on your calculator. Any calculator that you have, a scientific calculator, has E in it. All right. It's a number, but it's irrational. And it typically you'll see E with an exponent to it. And how do you figure it out? Well, your calculator has E in it. So you just click the E button and then type in the exponent. So let's look at what this probability is saying. Now this lambda, this is Greek letter lambda here, is the mean or the expected number of occurrences over a given time span. All right, the given expected number of occurrences over a given time span. Now, sometimes in many of these Poisson problems, they'll give you that. They won't call it lambda, by the way. They'll just call it average number of times this thing happens over time. All right, it's a count, average number of counts. Sometimes they'll give you a rate, right? A rate per item, and then they'll give you the number of items, and you have to multiply the rate times the number of items to get this lambda. All right, and then E. X is the number of what? Number of times that you are predicting you will see it over a given time span. Okay? Lambda is the expected number of occurrences. In other words, the average number over a long period of time. Here, with X, you are predicting the probability if you got this number over the time span, what would be the probability? So they're giving you the average number over a long period of time, but they're saying, what if you got this number, not the average number, but some other number? What's the probability of that occurring? See what I'm saying? So if you have, let's say let's say lambda is 1.2 calls per minute on a call center, all right? You have a call center, right? You get 1.2 calls per minute. I don't know, maybe it's per second, who knows? Let's say per minute. That's lambda, okay? But what if they give you the number of calls? What if they give you a rate, right? So many calls per hour, right? And then they give you the number of calls that happen during that time period. You can multiply those two things and you'll get an estimate of the average number during that time period, okay? We'll see an example of that in the problems. So this is Poisson. And it's easy to calculate once you know how to do this. And I believe Excel has a Poisson thing to estimate, but you can calculate this with your calculator. It's not that hard to do, all right? Why? Because X is going to be given in the problem. They're going to say, they'll give you X, the number of times this event happens. So the denominator is, once you plug in X, that's fixed. E to the negative lambda, well, lambda's fixed in the problem. That's fixed. The only thing that you're calculating that's varying is, well, actually, that's not true. So e to the negative lambda is fixed, no matter what X is. And then these two terms here, you just plug in X and you get your answer. It's easy calculation. All right, really, it's piece of cake. So the calculation itself is very easy. It's not like the binomial where you have, you have this combination thing and you have the probabilities to this power and that. This is very easy. You literally just need to know lambda and x, and you plug it in, and then you calculate. It's a piece of cake. Just the only thing you have to do is recognize it. Here's an example right here. In an urban county, healthcare officials anticipate that the number of births this year will be the same as last year. When 438 children were born, an average of 438 divided by 365, or 1.2 births per day. Okay, so 1.2 is the lambda. That's your average number of births per day. Why is it the average number? Because there were 438 children over the whole year, and there's 365 days per year. So wouldn't you say that's sort of an average per day? Yeah. So this is lambda. That's an average per day. So that's your lambda, okay? And then they ask the following. Use the Poisson formula to find the probability that x is equal to 0. Well, what does that mean? That means, what if on a particular day you didn't get any births? Let's look back at the original problem. There were 438 births in 365 days. Does that mean that there were births every single day? Does it mean that? We don't know until we actually see it, right? You'd have to look at every day to see how many births there were that day. There might have been 10 births one day, and 0 on another day, and 3 one day, and 5 another, right? Right? So what they're saying is, pick a particular day at random. What's the probability there were no births that day? That's P0. So you plug in 0 for x, and so your lambda to the 0 power times e to the negative 1.2, because it's e to the negative lambda, and the denominator is 0 factorial, which, by the way, is 1. So make sure you understand 0 factorial is not 0, it's 1. So the answer is 0.3012. What if they ask you the following question? What if you picked a day at random? What's the probability you had 2 births that day? Well, 1.2 is your lambda. X is 2. So it's 1.2 squared times, again, this number doesn't change, e to the negative 1.2, but the denominator becomes 2 factorial. So what is what is 1.2 squared? 1.44, I believe. Divided by 2 factorial, which is 2. That's what? 0.72. 0.72 times e to the negative 1.2, which is this number here. So 0.72 times 0.3, what is that? About what? 0.216, something like that? Whatever. This is a Poisson process. Not that hard, right? It's not that hard. You just have to recognize it for what it is. The real issue is, and I'll just point it out to you, because I was looking at many of these problems before earlier this afternoon, later this afternoon. The ability to recognize it. For example, let's see if I can find one, because I was working on this, and see if I can find it. Yes, 55. This during 2007, the crash rate for commuter air carriers was 1 per 100,000 flying hours. The crash rate. So they're giving you a rate here. Assuming this rate continues, in other words, going to continue into the future, what is the probability that there will be no more than 1 crash in the next 50,000 flying hours? Now, when you look at this problem, does it look binomial?
It kind of does to me.
Why? What is the probability of success?
because you're measuring or you're looking for the number of failures. Yeah. The probability of success would be 900 or 99,999
Okay.
flying hours.
All right. Suppose we did this as a. I see where you're going, Steve. It's clever what you did. Try this. You have your calculator with you?
Yeah.
You know how to use your calculator to find binomials? Maybe you don't.
I mean, I could put the
But
equation in, but
well, here's the deal. What is n in this case here, if you are correct? What is n? The number of trials.
100,000 or no, 50,000.
50,000. Okay. So 50,000 trials. And what's the probability? There will be no more than one crash. That means 0 crashes or 1 crash.
Right. So I guess
So n in your binomial, the number of trials is 50,000 trials. Let me try it with my calculator. We're going to do it as a binomial, all right? And I'm going to just tell you what the answer is here, or if the calculator can even do it. Maybe it can. So I'm going to put 50,000 for the number of trials. You could do it in Excel too. And the probability is what? 1 out of 100,000, right? So that is that 4 zeros and a 1, I think? 0.0000. Yeah, I think so. 0.0001. And then I want to know, for example, what's the probability of getting 0 crashes, right? So I'm going to put 0 in for X. Let's see if it comes up with an answer. Yeah, it does. 0.6065. Okay, 6065. Now, I want you to do the following. I want you to consider this a Poisson instead. All right. The rate, 1 out of 100,000. I want you to multiply 50,000 times that to get lambda. Lambda would give you, by doing that, you would get what? You would get the number of crashes.
0.5.
0.5. So if you do, if lambda is 0.5, right? Right?
Right.
Okay. See what you get for an answer. 0. You get, well, basically get e to the negative 0.5 power. Let's see if it matches this. Pretty close. Pretty close. So the binomial, the Poisson actually is a pretty good estimate for the binomial. If you can use the binomial, all right? The two come up with pretty similar answers. My calculator, 0.6065, and then for the binomial, the 2 digits after that is 29, and for the 2 digits after in the Poisson, it's 31. So pretty close. So you could do 6.55 as either a binomial or a Poisson, and you get the same answer. Yeah. Okay, is that good?
Well, when you did it with the Poisson, did you add up the probability of p at 0? And
No, I was just looking at probability of 0.
Oh, okay.
The question is asking for adding the probability of 1 too.
Right. Okay.
You could see it probably is pretty close.
Right.
Also.
Yeah.
All right. So that's good. So let me give you another example of a Poisson and see if it makes sense to do a binomial there also. So let me find one because I did quite a few of these. Oh, here we go. 6 6.67. Yeah. No, that's not it. Sorry about that. There's another one here. Yeah, actually, let's look at 6.67. This will be the last thing we do. I know it's getting late, so I don't want to keep you on too much longer. All right, let's read the 6.67. A producer of copper tubing, is this the right one? Yeah, has found that on the average, 5 flaws occur per 2,000 feet of tubing. The tubing is sold in continuous rolls of 200 feet each. What is the probability that a randomly selected 200-foot roll will have no flaws? My question to you is this type of problem more conveniently done through Poisson, or can you also do this with binomial?
Seems easy to do with the Poisson.
That's right. So in this case, you want to use that, right? You want to use Poisson. So what is lambda in this case here? What do you think lambda is in this case?
0.5.
Yeah, because it's 5 flaws per every 2,000 feet, right? That's 1 out of 400, right? So if a roll is 200 feet, the 200 times 1 divided by 400 is 0.5. Little tricky here, right? Little tricky. You have to be careful with this one. Now, if you put in x is equal to 0, which means no flaws, right? The answer comes out to be 0.6065. Now, here's an interesting part of this question. Let's look at 68. A large plumbing contractor buys 8 200-foot rolls from the producer described in exercise 6.67. Determine the probability that no more than 3 of the 8 rolls will be flawless. How would you do 6.68? It's a continuation of 6.67. So 6.67, what you calculated was the probability that 1 roll has no flaws. Now, somebody is buying 8 of these rolls, and they want to know what's the probability that no more than 3 of the 8 rolls will be flawless. How would you answer that question? What probability distribution would you use for that one? We won't go through the math of it, but I just wanted to make sure that you see how that works. And anybody can answer that question. We've calculated the probability that a randomly selected 200-foot roll has no flaws, and we used the Poisson to come up with that probability. Now somebody's coming along and buying 8 of these rolls, 200-foot rolls, from this producer. What's the probability that no more than 3 of the 8 rolls will be flawless? We're going to assume what? That the probability doesn't change. It's the same for any of the rolls. So what probability distribution would you use for 6.68?
Binomial?
Binomial. It is absolutely a binomial. It's just 6.67 answered the question, what's the probability for one of the rolls being flawless? Once you have that, that's the probability of success, right? Then the next question says, all right, we have 8 of these rolls picked at random. What's the probability that no more than 3 of them are flawless? Well, we now know the probability of success. Then 8 is the number of trials, because there's 8 rolls. And then we're going to use the 3. This is the probability that x is less than or equal to 3 for a binomial. So we're going to use the cumulative function, right? The cumulative distribution function. In other words, go back to Excel. Remember when we did the binomial distribution, there was the third option there, and it was either true or false, right? False meaning it's just one probability, true meaning it's the probability X is less than or equal to that number for X. That's what we'd use to solve this question. All right. So what I'm teaching you, I would never teach in a Math 111 class because you're all advanced. You've proven it to me. All right. You're proving it to me. So I'm showing you something a little more advanced because if you grasp these probability distributions, then you're going to understand inference really, really well. You're going to understand it really well. You're going to understand why things are done the way they are done. Most students have no understanding of this, literally, in the beginning, and then they're thrown into inference and they're completely lost. Many students. The only ones who do well on it are the ones who memorize very well. In other words, they mimic what teacher's doing. But if you have a good understanding of this, you don't have to mimic at all. I wish I was my teacher when I was younger learning this, because I didn't learn this way. It was much more difficult. You're just given a bunch of problems, they solve it. Good luck. Your test is coming up next week. All right, anyway. We have that extra day in the schedule, right? I believe we have an extra day. What we're going to do on Tuesday is we're actually going to work through many of these questions. Some of this earlier questions, which are simpler. I'm going to work through all the different types of questions I can ask you. I can even assign some homework in addition, if you'd like. And then on Thursday, we'll go into chapter 7, which is the most important chapter in all of this. That's the normal distribution. All right. So we'll do that on Thursday. At least start on that chapter on Thursday. Okay. Any questions? And there will be also a quiz coming up, but when I have to give my Rowan students, I have a test and quiz I have to write this weekend. So I'm not going to get to the quiz for you guys until next week for chapter 5 and 6. But I don't think you care very much, right? Yeah. All right. Any questions about what we covered tonight? Was it useful? I mean, what we went over, was it useful? All right. So hopefully you'll have a better understanding of what probability is once we've completed chapters 6 and 7. Then inference, I believe you'll understand it much better because you'll have a good foundation in probability. And I think you should be very successful for the rest of the course. All right. And don't worry about me giving you really difficult questions on your test. I'm not going to do that. I'll give you basic ones. All right. If you can do the difficult ones, you'll be able to do the questions on the test. All right. Any questions? All right. So I'll stop sharing, and if there's nothing else, I will see you on Tuesday. Okay. And I believe I gave you a short homework assignment from chapter 5 to complete, right? Have anybody's completed it yet?
Not yet, no.
Yeah, it's easy to do. Should just take you an hour, maybe no more than an hour to complete it. So maybe a half hour if you know the stuff. All right, that's it. So I'll see you next Tuesday. All right. Have a nice night.
You too.
Yeah. Bye bye.
Professor?
You too. Bye bye.